Hello, welcome back, and this is week 3 of combustion control circuits, which is EST-101. This week I will try to cover some of the oil storage basics and some tank inspection. So this is part of NORA book, and I will also cover chapter 14 that has to do with some basic controls for furnaces and boilers. So there's a lot of material to cover. Please take note and pause when you have to. Again, in this course I will throw a lot of information regarding oil heat, gas heat, and basic control. Okay, let's start. Okay, didn't click. Let's start now. So again, chapter 3 NORA book, oil tank, some regulation. Again, if you are going to take the oil burner license, you will have to know these codes and these terminology. So I'm going to go through over some oil storage fundamentals, and also I will go over chapter 14 in the electricity book. Let me just fix the camera here. Okay, I think this is good enough. Okay, all right, moving on. We'll talk about explain combustion basics. That's ignition, fuel, and heat, and what we get out of that. We will identify the oil delivery types. How do we deliver oil to the system? But I'm not talking about delivering oil through truck into your storage, but from the tank to your system. Components of oil pump system. Recognize tank and piping codes. What are the codes and what is needed to have for the tank to be inside the house or outside. We'll differentiate, or not differentiate, not differential. Differentiate between types of residential tanks. Let me fix this while I'm at it. This is bothering me. Differentiate. Okay. And this delivery. Okay. Differentiate between types of residential tanks. What kind of tanks do we have? We have indoor tanks, we have outdoor tanks, and we also have below ground tanks. There are codes concerning each one of them, and you will be asked about these codes when you do the oil burner technician license exam. And where would you find this information? It's in the CMR 51, I believe, and I will attach that into the blockboard so you can review. We'll classify tank inspection items, and there's a video, 20 minutes video, that you will watch for you to learn a few tips about oil tank inspection. Okay, moving on. Let's try to fix the camera here. Okay. List what kind of limit switches are there. Let's get on with it. Combustion, we need always to have the correct mixture of fuel and air. Why? We did say that repeatedly. You need to have the right amount of air to fuel, otherwise you will have smoke. So we need not too much air and not too little air. We need the right amount of air to have complete combustion. What is atomizing? Atomizing is breaking down the fuel into small little droplets, and we're talking about fuel oil because it's liquid. When it comes to gas is already atomized. You don't need to go through this. What is clean combustion? We just said that. Clean combustion is when you burn the exact same amount of air to the same required amount of fuel. So there is no excess air, not too much, not too little, and so on. What is the ignition point of fuel oil? We covered that last week, that it's a temperature, and it's 550 degrees Fahrenheit. This is when the fuel will start to ignite and continuously ignite. 500, I've seen 500, 550, and also I've seen 600. Depends on the fuel and its grade, but for fuel oil number 2 to meet specification, it has to be around 500 degrees Fahrenheit. This is an old schematic about oil burner types and how the oil get delivered from the storage to the combustion chamber. If you look here, this is the oil pump. There's an air pump that pressurizes the fuel. Again, this is a very low pressure atomizing burner, where there's a different pump for the air and different pump for the oil, and they both get pumped in together. There's also vaporizing wicks that do the same job as a candle or an oil burner with no pressure. Basically use osmosis to draw oil from a reservoir into the burning location. Some of them are also gravity fed, so you put the tank in a level higher than the wick and the oil just seeps through the wick and get lit. There's issues with soot, of course, if the wick gets overfed or there's not enough air, so it's not as efficient, but it does still work, and in some locations it's still used for a location when there's no electricity. Especially it's used in France and Japan for places where there's no electricity and there's a lot of earthquake and there's issues with storing oil. So it's very old-fashioned, but it's still used and it's very efficient. And it's something to think about if you are going to have a cabin in the woods and you don't have electricity and you want to have oil heat. It is possible to use a wick system. Low pressure burners are considered between 1 to 15 psi, and this has to do with the pressure coming out of the steam. So this is for steam, it's not the pressure of the oil. You can either pressurize the oil or introduce pressurized pressure into the system. So I put this in different colors to differentiate that the pressure has to do with the oil, but the pressure of the steam coming out of the burner. But to pressurize the oil inside, you will maximize the amount of spread of the oil, so you can pressurize either the oil, and we did that last semester in the lab where we measured the oil pressure for the pump, and sometimes we also can pressurize the air. How does that happen? It kind of look like when you spray paint. You have a pressurized air and you pull air using negative pressure. High pressure boilers, they usually have larger fuel pumps with high pressure, more than 100 psi, mainly industrial. They have not changed in operation in basic operation since the 1930s. They did change in terms of control, but the boiler technology is still the same. Few changes in terms of transformers, nozzles, and burner size, not that much, but the control has advanced significantly. Nozzle and flame shape relation, that's something we would like to talk about. Again, the book does spend some time on that. I don't know what is the big deal. I think the big deal has to do with lower SOx and NOx, which is nitrogen oxide and sulfur oxide. So there is something called the stabilizers or chokes or diffusers or turbulators, and basically it's the blades or plates that are placed in front of the nozzle to shape the flame. So the flame takes a different kind of shape just to have it combust in a very efficient manner. If you take the course at Mystic, they will talk a lot about the size of the flame and how is this very important when it comes to low NOx and SOx. So you see in this picture over here, you have the flame completely contained, all put together. Meanwhile, if you look at the flame over here, you'll see how the flame is all over the place, and those little flames actually they combust in different ways. There's a lot of science and chemistry that goes into the flame shape and how does it react with the air and how does it dispense different kind of fumes. I don't want to go too much into the science of it. For you, you need to understand that the diffuser plate that's placed in here does make a difference. Here it is. Distance between this flame and the nozzle is also very calculated. Okay, it came in the 1960s. Flame held close to the burner. Some of the retainer provide a swirl. Okay, that's kind of cool. Tornado effect. They did improve efficiency from 5 to 15%. That's a little bit significant over a period of time. Okay. More heat, less excess air. That sounds kind of cool, right? We don't want a lot of excess air, we want more heat. Increase the temperature from 300 to 500 Fahrenheit. That's inside the combustion chamber. That's a little bit significant, and I think it's worthwhile. Smoke is reduced to 0 or almost 1 versus to 2. What does that mean? Smoke 0, smoke 1, smoke 2. There are levels of smoke. Basically, when we do the smoke test, you will use some kind of a tissue paper that you put in a plunger, and you pull in the plunger 10 times, and you compare that color to the clear color of tissue paper. So there is 0 smoke when there is no color at all, or 1, that's acceptable, and in the pad it used to be 2. So 2 is bad. So now we want to aim for 0 smoke. 0 smoke, that means that we burn the fuel in a better way than we used to. Okay, it's still an active area of improvement. You might be able to come up with a new kind of turbulator, or you might see new ways for turbulators or diffuser plates on burners. Okay, moving on. Fuel pump and igniters. Again, I'm trying to touch base on all these subjects slightly. So touch base on strainers. We did cover that when we did the lab for the pump, and I'm just trying to give you a kind of refresher on those components. So strainers, let me move on. Fuel filter, we said there has to be a fuel filter before the pump. It will save your pump life, and it will capture all the stuff that are trapped into the tank. Regulator valve. This actually has to do with the fuel oil coming from the tank to the pump. There's another valve, it's called the oil valve, that comes from the pump to the nozzle, and this to regulate when the oil start to flow inside the chamber. For igniters, we have a transformer that goes from 120 all the way to 17,000 volts of spark to ignite the oil. So this spark will provide around 600 degrees Fahrenheit to start the spark for the oil. You need, this is also nice information, you need 30 cubic feet per minute to burn 1 gallon per hour per minute of fuel. Let's pause a second here. So for 1 gallon per minute fuel, you need 30 cubic feet per minute. So again, you see the ratio is 30 to 1. So you're not gonna burn 1 gallon per minute of fuel. Usually you'll have maybe 0.5 gallon per hour. So for 0.5 gallon you will need 15 cubic feet equivalent amount of air. So that's why when you turn on the boiler, you hear the fan sucking a lot of air from the space, and that gets you to think you have to provide a lot of makeup air for the boiler to act properly. I repeat, the ratio is 30 to 1 gallon if you want to compare gallon to gallon. Sorry, cubic feet to gallon. So you have to convert cubic feet to gallon. It's a good ratio to know, to have an idea of how much air is required to burn 1 gallon of fuel. I think I did a conversion at some point, but it's very important to have some nice good makeup air coming inside the boiler, especially if you are going to pull air from the living space like the house or the basement. Moving on, these are some of the components. We went through this last semester. Just to reiterate, we have a motor, inducer fan connection. So the motor turns on the fan. This is a coupler, and this coupler does connect the motor to the pump. This is the air belt where we allow the air to come in. The nozzle assembly in here, the diffuser plate, and transformer, and this is the housing. Excuse me. Okay, that's kind of a review for the components that we have for oil burners. Please try to skim over chapter 1, 2, and 3 in Nora book to give you an idea of stuff that we already did. There's a lot of information provided in the book to shed light on these components, and it will be very helpful for you to know where this information are located when you're doing your oil tank repair or oil burner repair. Tags and piping, these follow the code for NFPA 32. I think I do have that in the reference in case you need to look at it. CMR 31, sorry, I did say it was 55, but I think it's 31 and they keep getting updated. So I put the most recent one in the blackboard. For tanks, it does state, and this has not been changed so far as I know, it's a 660 gallon maximum size of tank. So if you are going to have above ground tank, it has to be the maximum size of 660 gallon. However, you can have two tanks, which means you are allowed to have two 660 gallon tanks connected to each other, and that will be around 1320 gallons. So you cannot have more than 660 gallon above ground, period. You can have underground tanks that can be bigger than that, and the maximum amount of oil you can have in any building, whether residential and commercial, is 10,000 gallons. Locations can be inside, it could be outside. There are different codes for each one of those. Inside building, it could be in a basement, boiler room, or a garage. There are special installation techniques for each one of these. It could be outside above ground or outside below ground. There are codes for that as well. Underground has more, it's more expensive, of course. It has to require different kind of installation procedures, and it has to be insulated, of course, and there's regulation for the distance that you should be aware of. Why? In case you work for a place where they want you to fill oil, you have to know these regulations so you can determine if this is per code or not. Inside tanks, they have the advantages. They are a little bit low cost. They can be fiberglass. They have longer life. Why? They are not exposed to the elements. They have uniform temperature because, again, they are inside, they're not outside. They are not getting subjected to a lot of variance in temperature or wind. Stratification, that means the layers of the oil. So you know that oil does change density with temperature. Over time it can be stratified, which means like you have high density oil in the bottom, low density oil at the top, etc., based on the temperature. So when the tank is placed inside, probably it will have better stratification and better uniform temperature. If you put the tank outside, you are going to subject the tank to a lot of cold temperature, which could be a problem because in the winter you have to pump this oil inside, and we did say from last class that the porosity, no, sorry, not the porosity, that's the different terms. The pour point for oil, which the point where the where the oil is liquid, is around 20 degrees Fahrenheit. So anything below that in the oil is going to crystallize, and this temperature does get cold, especially in places where we use oil like New England. So it's good to keep the tank inside, and sometimes you might have to heat that tank even though it's inside. Viscosity, we say it does change with temperature. Tank location codes. There are some codes here that I'm going to throw at you from what I've seen from the questions. I want you to remember these codes. Let's look at these codes a little bit. Let me see if I can change the camera here. Okay. The tank has to be at least 5 feet from the burner. So if you're going to have the tank inside the house, in the basement, make sure it's 5 feet from the burner, 5 feet from even the washer and dryer. So that's one of the numbers. The vent has to be at least 2 feet from any other opening, and this is the vent for the tank. Size of the fill pipe and the vent pipe. The vent pipe has to be bigger than the fill pipe by at least 15%. So hopefully you remember that. 15% vent pipe is bigger. Okay, valve, tank valve, the outlet. Tank has to have a valve and an outlet that let the oil comes in. Swing joint. This is a swing joint. I put it there so you just understand what it looks like, and it has more elbows, and the purpose of having a swing joint is the expansion and contraction. If you have a pipe between two tanks that is rigid with no elbows, the possibility of you dislocating connection is very high. Swing joints give you some flexibility for the tank to expand and contract by a few millimeters without affecting the connection between the pipes. Filters are important and required. Tank gauge are preferred, not necessary. If you're going to have a glass gauge, make sure it's going to be in the top, and you can have a glass gauge as long as if that gauge breaks, you do not lose any fuel. Must stand on concrete floor and legs, so you cannot have the tank standing on wood or carpet. Must be on the lowest level of the building. That's obvious because it's going to be very heavy, right? Thermal shutoff valve. We've seen thermal shutoff valves. They look like the pyramatic valves that we had on the board. It's a valve that will melt at 165 degrees Fahrenheit and shut off the oil flow. Secondary thermal valve is 15 feet. So you will need a secondary shut-off valve or thermal valve at 12 feet if you have oil going more than 6 feet on top, or if you have a ceiling that's really that high. So if the ceiling more than 9 feet, probably gonna have 2 thermal valves instead of 1. But most ceilings are around 9 feet. So just keep that in mind. Here is a snapshot from the CMR and the connection and some of the terminology they have. So we have tank 1 and tank 2. Each one of them can be maximum of 660 gallons. Plug that you will fill from one tank and the vent will be from the other tank. So the first tank will fill up, then it will you can keep filling, and you can fill the second tank as well, and those tanks will be connected to each other with a swing joint, and you can see the elbows in here, ground joint connection, and so on. Okay, moving on. Outside above ground tanks, why would you do that? Sometimes you don't have space inside, and there's no, you don't want to put that in a living space. It has to be in a basement or a garage, so you don't have dedicated space for the tank, so you might have to put it outside above ground. It has to be at least 5 feet from the building. Again, it has to this code varies from one place to another. I've seen them not 5 feet from the building, but it has to be 5 feet from any living space for the vents and the fumes coming out of the oil. Problems with moisture, cold, and dust. You have to provide some kind of shelter for that tank because it will be subjected to all these things. It has to be in a location. If it's going to be in a location that's below 20 degrees Fahrenheit, you have to add 25% blend of kerosene in the winter. So probably this is going to be all over New England. It does go below 20 degrees Fahrenheit, so you might want to add a blend in the winter, otherwise it will freeze. Piping. Copper pipes with PVC. So usually when we connect oil lines, they're mostly copper because copper is resistant to corrosion. So it's a good idea to do that. The PVC is recommended, especially if you're going to bury that line. So remember that for the oil bearing license. They will ask you what kind of pipes. It should be copper pipe, and it should be used flare joint, not welded, not threaded. Never bury a copper pipe without the PVC. It has to be connected with PVC or sheathing. For average oil burner, the inlet should be 3/8 outside diameter. That's the average size of the pipe. All copper fitting should be flare, no press fitting or solder fitting. Never use Teflon. You can use different kind of tape that's specialized for oil, but no Teflon. Use one pipe size, minimum of 3/8, but try to have uniform pipes oil line size because that kind of minimizes the pressure drop or increase. It should be tight and leak proof, and always check for leaks throughout the system. If you have threaded connection for any reason, you have to use a special compound that is oil resistant. Okay, underground tanks, they must be 2 to 3 feet deep. Suction and return should be installed 3 inches to the bottom of the tank to enable switching. This is again a snapshot from the CMR, and this is the swing joints and the depth of that tank, 2 to 3 feet from the top of the ground, and you should be able to be switched from filling and venting as well. Okay, since some code from NFPA, vent and fill line should terminate outside the building at least 5 feet from any building opening, that's windows, door, or kitchen vent. The fill vent should be smaller than the fill pipe. Should not, I was like checking that, it should not be smaller, should be bigger by at least 15%. They should be weatherproof, and they have caps on them and mesh to eliminate the intrusion of insects. Steel schedule, types, more. Vent pipe on 660-gallon tank must be at least 1.5 inch higher than the fill pipe. More piping. When the tank is higher than the burner, an anti-siphoning valve must be installed. It's called PRV. Again, we rely on gravity to pull the oil from the tank to the burner. If not, we might have to install a valve or have a anti-siphoning device or a loop, because if you empty the tank completely, you have to fill that pipe to prime the pump, because the pump for the oil is not designed to pull oil. We've been through that before when we did the pump testing. Thermal valve must be installed on the suction line before the filter, and it melts at 165 Fahrenheit. How does it work? Again, it melts. It has a valve and counterweight. Whenever there is heat, the solder will melt and the valve will drop the stem and shut off the flow. Gauges must be installed in all inside tanks. That's according to the NFPA. Tank failure. The average lifespan of the tank is between 10 to 15 years, depending on the manufacturer and the warranty. Location, thickness, buried or underground, or maintenance. They all matter on the lifespan of the tank. There's a lot of tanks that you find inferior, and you should not be filling them, especially if they're very flimsy and thin walled. There's some low quality steel tanks that should not be used. Fiberglass are very common these days to install. They're very inexpensive and they last a little bit longer than steel. If you bury the tank in acidic soil, it might be more susceptible to corrosion. Water. If the tank is dented or mishandled, it's most likely to start to rust and deteriorate. Again, tank and product worst enemy is water. Water causes rust. Water also promotes the growth of bacteria and gumming of the product. More information about the pump. We did checking the pressure, checking the vacuum, any leaks. Be aware of grinding noises in the pump. We did cover that during the last semester's lab. Things to look for: if the pump is pulsating, that means the filter is clogged or there is a kink in the oil supply line. The pump must be positive displacement shut off, if not gas. What does that mean? So the pump must be positive displacement, meaning should be able to push the oil through, because again it's going to be subjected to a lot of pressure, almost 100 psi, and if the oil is clogged, it should be able to shut off completely. Okay, for more what if scenarios, look at page 423 in the book, and there's a flow chart for all the pump issues. Okay, you'll see now the tank inspection video that you can watch on the blackboard later on, and these are some notes that you should have registered from that video afterwards. Please just skim through it. I know it's a lot of information, but I will stop the video right now, and this should be enough for this week's material on NORA book, and I will let you skim the stuff for chapter 14 on your own. Alright, thank you.